We investigate generalizable tumor segmentation, aiming to train a single model that can not only segment tumor types seen during training, but also generalize in a zero-shot fashion to unseen tumor categories, thereby enabling tumor segmentation across diverse anatomical regions. With the advancement of medical image segmentation techniques, an increasing number of methods have focused on multi-tumor segmentation. However, these approaches depend heavily on fully annotated training data sets, which limits their ability to generalize beyond a narrow set of tumor categories. Some methods leverage vision language models to align lesion regions with textual descriptions in an attempt to generalize to unseen tumor segmentation. However, these approaches often suffer from limited segmentation quality due to the scarcity of high-quality image text pairs for training and because the contrastive learning-based alignment process is not inherently optimized for pixel-level segmentation, as its objectives do not directly target spatial and relational understanding. Another promising direction towards generalizable tumor segmentation is tumor synthesis, which enables label-free tumor segmentation by creating artificial yet realistic medical images. However, current tumor synthesis methods are unable to encompass all tumor types, as simulating tumors with irregular shapes or those not encountered during diffusion model training poses significant challenges. Motivated by the above challenges, we take an innovative approach towards generalizable tumor segmentation. Our key insight is that despite the challenges in simulating tumors, a medical foundation diffusion model, MFDM, trained on large-scale data, is capable of understanding rich, diverse anatomical structures and organ-specific knowledge. Moreover, this valuable knowledge is already embedded within its internal representations. While directly synthesizing a wide variety of tumor types may be challenging, synthesizing healthy organs is relatively feasible with medical foundation diffusion models. The tumor region can then be obtained by computing the discrepancies between the input image and the synthetic image. Thus, the crux of the issue becomes how to enable the model to detect diseased organs in a zero-shot manner, generate their corresponding healthy counterparts, and then achieve generalizable tumor segmentation. We propose DiffuGTS, which fully leverages a pre-trained medical foundation diffusion model to achieve generalizable tumor segmentation. First, DiffuGTS employs a novel text-driven anomaly detection technique, Anomaly-Aware Open Vocabulary Attention, AOV maps, to repurpose internal image representations from a frozen foundational diffusion model for zero-shot tumor localization and detection. Next, for each localized diseased organ region, DiffuGTS uses a novel training-free latent space in painting method to synthesize its healthy counterpart. Finally, by applying pixel-level and feature-level residual learning, we obtain the accurate tumor segmentation masks. In practical use, DiffuGTS begins by applying a range of text prompts to detect anomalous regions within the image. Once these abnormal areas are identified, it synthesizes pseudo-healthy versions of those regions. By comparing the original image with its synthesized counterpart, DiffuGTS then accurately derives the tumor segmentation mask. By effectively leveraging the rich anatomical features embedded in a pre-trained medical foundation diffusion model, DiffuGTS can perform zero-shot segmentation of tumors across organs and even across imaging modalities, achieving generalization from CT to MRI, a capability absent in previous methods. Furthermore, DiffuGTS's zero-shot segmentation performance far exceeds that of all existing medical segmentation models and even approaches the level of a fully supervised, task-specific segmentation model.